So in this question, we're told that we have a geometric series and it has a common ratio of r and its first term is a. We're told that the common ratio r is not equal to 1 and that a is not equal to 0. And we're asked here to prove that s of n, so the sum of n terms of our geometric series, is equal to a multiplied by 1 minus r to the power of n, all divided by 1 minus r. So just to start, we will have a think, what is Sn going to be? So we'll write Sn, so we know it is going to be the sum of all the terms. So we're going to just write this out in full, and then we can work with it from there. So we know that our first term is a, so we'll write a down, and then to get the sum of our first two terms, we're going to add in the second term. So what is this? We have a common ratio of r, so it's going to be the initial term a multiplied by r, because that's our common ratio, and then we're going to then have our third term, that's going to be a, then this time we multiply by r again, so we have ar squared, and then we have ar cubed, ar to the power of 4, and so on, and we have that this goes all the way to a multiplied by r, n minus 1. So we stop it at n minus 1 here, and that's the final term of our geometric series. And that's because we're summing up the first n terms. So for example, we have 1, 2, 3, and so on, and this is our nth term here. So that's the sum of our nth terms. So what we're going to do now, just to manipulate it, we're going to multiply both sides by r. So we'll just write in times r here. So therefore, what does this give us? This is going to give us r multiplied by Sn, and that's going to be equal to, well, we'll multiply each term here by r. So we'll have the a turns into an ar, the ar turns into an ar squared, and then our third term is going to be ar cubed, and then we add on all the way up to a to the power of r, and this time we're going to have one extra r effectively, so it's going to be ar to the power of n instead of n minus 1. So the next step is we want to find the difference between this equation here and this equation here. So we'll have the sum of our n terms, and we'll subtract r multiplied by the sum of n terms. So then this is going to be equal to, well, we'll have our a plus ar plus ar squared plus everything all the way to ar n minus 1. And then we're going to subtract all of these terms from this equation here. So we'll have negative ar squared, and then we'll subtract everything all the way up to ar to the power of n. So we now need to have a think what terms cancel out here. So we see we have an a here, but we have no a on the other side. But then we have an ar and a negative ar. We have an ar squared and a negative ar squared. We have an ar n minus 1, and in here we'll also have an ar n minus 1. So this means this is going to leave us with only this. So we'll have our a here, so I'll just highlight that in yellow, and then it's also going to leave us with negative ar to the power of n, because as we know the nth sum ends at ar n minus 1, which leaves this term here also. So therefore we can write this in a simpler form. So the n sum minus the r multiplied by the n sum is going to be equal to, well, we have a, and we're going to subtract ar to the power of n. So then now what we want to do is we want to take this equation here and we want to rearrange it to get this equation here. So I'll just write that in. So we now want to rearrange to get the required answer. So what we're going to do, well, we're going to take a look at this left-hand side. We're going to take a common factor of n out. So the n sum will take a common factor of that out. So that's going to leave us with the n sum. Then we'll have 1 minus r. And this is going to be equal to, well, what can we do on the other side? We can take a common factor of a out. So it's going to leave us with a lots of 1 minus r to the power of n. So in the next stage here, we can see this is very much getting into where we want it to be. So then we're going to divide both sides by, well, 1 minus r, and this will leave us with, so we'll have the nth sum of our geometric series is going to be equal to, what's our right hand side, so it's a lots of 1 minus r to the power of n, and then we now are saying we'll divide everything by 1 minus r, and that gives us the required answer which we were after in the question. So we'll just write in as required. And therefore, we have completed this question, and we've proved that the sum from the first n terms of our geometric series is going to be a lots of 1 minus r to the power of n, all divided by 1 minus r. So where did we pick up our marks? So we received our first mark for writing out the sum. So that's when we wrote out our list of terms here. So that's our first mark we achieved there. We then achieve our second mark for knowing to multiply the sum by r. So that was at this stage here. This was a key stage which helped us move forward with the problem. We then receive our third mark for writing those terms out and simplifying it to get to this stage here. That was when we had the n sum minus the r multiplied by the n sum was equal to a minus a to the power of rn. So essentially from here to here we get this mark for cancelling out these terms, and we then receive our fourth and final mark for concluding with the correct answer, and that was the answer which we wanted to prove in the question. So in this part of the question we're given some further information, and we're told that the sum of the first 10 terms is 4 times the sum of the first 5 terms, and we are asked to find the exact value of r. And we also want to bear in mind that we've proved in part A that the nth sum is equal to a lots of 1 minus r to the power of n over 1 minus r. So what we're going to do here is we're going to write out what we're told in the question, and that's how we're going to start things off. So therefore, what we can say is that the sum of 10 terms is equal to 4 lots of the sum of 5 terms. So as you can see, we have S10 is equal to 4 multiplied by S of 5. So what we can do now is we can replace this here, S of 10, with this equation here, where we replace n with 10 on the left-hand side and n with 5 on the right-hand side. So therefore, what we can say is that a lots of 1 minus r to the power of 10 divided by 1 minus r is going to be equal to 4 lots of a multiplied by 1 minus r to the power of 5, and then we're going to divide all of this by 1 minus r. So what we're going to do now is we're going to essentially rearrange this equation, and we want to solve for r. So there are a few things which is going to make this slightly easier. So we see that we can divide both sides by a, and this a will cancel out, and this a will cancel out. So we'll just put in here, divide by a, and then what else can we do? So we notice that we have 1 minus r on both denominators. So if we multiply both sides by 1 minus r, like this is going to cancel them out, and therefore going to leave us with the following. So we'll have on the left hand side, so as I said, the a cancels and the 1 minus r on the denominator will cancel. So that's going to leave us with 1 minus r to the power of 10. And same on the other side, the a and the 1 minus r cancel out, so that's going to leave us with 4 lots of 1 minus r to the power of 5. So then what we're going to do now is we're going to tidy this up a little bit, and just working along the way here, we are going to expand the brackets on the right hand side, so we're going to have 1 minus r to the power of 10, and that's going to be equal to 4 minus 4 lots of r to the power of 5. So we're going to once again rearrange this, so we want to turn this into something which looks similar to quadratic. So if we rearrange this, we'll add r to the power of 10 to both sides. So we'll have r to the power of 10, and then we take away 4r to the power of 5, and then, so essentially we're moving everything to the right hand side here. So that means we have 4, and then we want to get this 1 to the other side, so we subtract 1, and that's going to leave us with positive 3. And that's all equal to 0 now. Apart from what I've done is I've just written it out on the left hand side, even though we've moved everything to the right hand side, and it's equal to 0. So either way, it doesn't really matter there. Then what I want to do now is I want to solve this for r, but this is slightly tricky. So what I'm going to say is then what we're going to do is we're going to then let x equal r to the power of 5, and then that means x squared is going to be equal to r to the power of 10. So therefore, this is going to make it easier to solve, so we substitute our values of x in. So we'll have x squared, then we're going to subtract 4 lots of x, and then we have our constant 3 on the end, and that's equal to 0. So we now have a quadratic, which is much easier to solve. This is much easier to solve compared to this. So what we can do is we can factorize this, and this is going to give us x minus 3 and x minus 1. And we know this is right because we can check our answers by multiplying it out. So x squared, and then we'll have minus 3x and minus x, which is minus 4x, and then we have negative 3 multiplied by negative 1, which is 3 here. So therefore, what we can say now is we can substitute our r values back in. So r5 minus 3, that like that, and r5 minus 1 is equal to 0. So therefore, next stage here, we'll now write these out explicitly, our values for r. So from this first bracket here, that's going to give us that r to the power of 5 is going to be equal to, well, we add 3 to both sides, which leaves us with 3. And what we want to do to isolate r is to take the 5th root, which is going to leave us with the 5th root of 3. And then we'll deal with our other r. So I'll just put an arrow here, and then we're going to have r5 is going to be equal to 1, which implies that r is going to be equal to the 5th root of 1, which is 1. But we're told in the question that r cannot equal 1. So we'll just write in here, but this solution isn't valid since r cannot equal 1. So therefore, this leaves us with our solution 5th root of 3. So we'll just write that in. So therefore, the exact value of r, and we know that it asks us for the exact value, so this means that we'll leave our answer in this square root symbol form. So the exact value of r is going to be such that r is equal to the 5th root of 3. And there we go, we've completed this question, and now we're going to take a look and see where we achieved the marks. So there was 4 marks on offer, and we do achieve our first mark for having the correct strategy and producing an equation which had r10 and r5 in it. So that was at this stage here where we achieved this first mark. And then we receive our second mark for working through the next stage. So knowing that things cancel out and getting to this point here where we had the kind of one line equation, so to speak, with no fractions. And we then receive the next mark for following through with this work and doing the correct algebra, which was when we did all of this work here and solved for r. So that was essentially at this stage here. And then we received the fourth and final mark for omitting the r equals 1 solution and concluding that the only exact value of r was the 5th root of 3. And therefore, we've completed this question.